This mini screencast is going to cover a topic that is covered later in the textbook, so we are going to depart here a little from the order from the textbook. We are going to cover the topic of dynamic memory allocation, which is pretty much the usage, the application of pointers to allocate and deallocate and reallocate memory during the runtime of your application. Okay, so far what we have been using is every time we need an array of integer, an array of double, an array of char, for example, we specify its size at compilation time. Now what happens if you want to write a little application that simply asks the user, well, how many grades do you want me to handle and compute the average upon? And the user is going to provide you with this number only when? Well, only during runtime, when the application is actually being executed. So in that kind of scenario, right now we cannot do anything. We are going to learn the tools that are going to allow us to allocate memory while the program executes. So here is our base case. We want to allocate one dynamic variable, and this is generally not going to be our most common case until we encounter data structures. With what we know so far, that would mean I want to allocate enough memory for one variable, an integer, a double, a float, a char, etc. Now what that means is that we need to be able to call a function which will execute at runtime, which will find somewhere the memory to give us, and generally this is going to happen, well, not generally, this is going to happen in the heap. Okay, so we already mentioned the text segment of a program, the data segment. We mentioned also the stack. We mentioned it a lot during our chapter on functions. Well, now we're going to pay more attention to the heap. Actually, the heap is a location in the address space of your executable where all the dynamic memory come from. So you call this function, the name of that function will be malloc, memory allocation, and this function will take as parameter how much memory you want, enough for an int, enough for a double maybe, and in return this function will return to you the address where a block of memory of the size you specified has been locked and blocked for your usage, and this is going to be located on the heap. Unlike all the memory that is allocated on the stack, which is disposed of automatically when you leave the block where it has been allocated, the function, for example, where the local variable of the parameters have been allocated, with dynamic memory, everything is explicit. You call malloc to be able to get some memory, and you will have to call free to be able to dispose of it. Another little difference, when you declare an array, let's call it data, of 33 integers as a local variable in one of your functions. As soon as you enter the function, the array is created on the stack. As soon as you leave the function, the array is destroyed on the stack. With a dynamic memory, no such thing. Everything is created when you call malloc on the heap and will not be destroyed until you call explicitly the free function. Okay, so there is no longer an automatic management of when things appear, when things disappear. You can return from a function that has called malloc, and the space that you reserved on the heap is still very much so allocated for your usage. Okay, now how do you use this space? Well, when you call malloc, malloc will return to you a pointer. We'll see more information about that in a second, but it's a generic pointer. So if I tell malloc allocate enough room for me to store a double, malloc will return to me the address at which is allocated enough space to hold a double value. And this is how I'm going to use this new dynamic variable, through the pointer in which I store its address. So you will see that every time you call malloc, generally the return value of malloc is stored in a pointer of the appropriate type, data type. Okay, and then you use this newly allocated variable through your pointer. So we discussed of this case so far, okay, using memory allocation to allocate one dynamic variable. It's really arguable so far what we would do with such a feature. Okay, if I want to allocate dynamically an integer, well, I can say that 99% of the time I could just declare it as a local variable and be off with it. Okay, so like it's indicated here, this is going to come handy later in this course, in the third part, when we cover actually data structure. For now, what is going to be much more useful for us is this part. I can allocate one dynamic integer, but I can also allocate n dynamic integers, which means pretty much I can allocate a dynamical array using malloc. How does that work? Well, from what I told you so far about malloc, when you call malloc, you say, I want this much space. For example, if you want just to be able to store a double value, you would ask malloc to reserve an amount of space equals to size of double. Well, because of malloc low-level nature, malloc doesn't know anything about data, it just knows how many bytes you want. You can ask malloc to reserve for you the size of a double times 30. What's going to happen? Malloc is going to return to you the address at which a dynamically allocated array of 30 double exists. And this is a lot more interesting for us right now. Okay, so we can, for example, prompt the user for a number. How many grays do you want me to store? The user types 99, and I'm going to call malloc to allocate an array of 99 doubles. If the user would have needed only 20 of them, I would just use at runtime the memory I needed. Once again, no way to forecast that at compile time, so really this is where dynamic memory allocation shines. Notice also, before we move to the next slide, that we cannot use any dynamic memory allocation if we don't have pointers. Malloc returns the address at which a new variable is located. You need to store this address in a pointer, and then you need to use pointer arithmetic to use your array through that pointer, your array or your single variable if you have allocated only one variable. So this is, in a nutshell, the logic behind memory allocation. Now, these are the functions that we are going to learn to use. There are different functions available in C, okay, some of them that even do some allocation directly on the stack. We're not going to look into these, okay? We are going to focus our attention on the dynamic memory allocation, which takes place on the heap. The four functions that you will have to know are malloc, free, realloc, and calloc. Malloc, which is the one, malloc and free are the one that we are going to use the most often in this course, okay? Malloc means memory allocation. Here is an example of code using malloc. You declare a pointer on int p, initialized to null, okay? And then you assign to p the call to malloc with the size that you request, size of one integer times 20, which means that the variable p is going to receive a pointer, a memory address, which is located somewhere. Let me draw a quick diagram here. This is your text segment, this is your stack, this is your data / BSS segment mixed together. We want to differentiate between them. This is your dynamic memory allocation area. When you call malloc, some of this dynamic memory is going to be locked for you, for your usage. Okay, it's going to be allocated to you, and this is going to be big enough to contain 20 integers. This address will be returned to you so that you can store it in your variable p. So somewhere on the stack the variable p is here, and p is assigned the address of this newly allocated block of 20 integers. Why this conversion here? You can remove it if you want. Okay, the real reason behind it is that malloc returns to you a pointer which data type is void star. The void star pointer, void means nothing, okay? The void star pointer is a sort of generic pointer. It means that it's capable to hold an address to anything. Address of an int, address of a double, address of a char, etc. Well, it's not magic. It just boils down to the fact that any pointer is a 4 bytes unsigned value. Okay, so you can store in a 4-byte unsigned slot a pointer on int, pointer on double, pointer on void, etc. Pointer on char, I meant. So since malloc doesn't know exactly what you want to do with the memory you alloc, and since it doesn't care about it, it just returns a pointer which is of type void star. Then it's up to you to explicitly convert it to the type that you need, for example int star, or let this conversion happen implicitly, because the C runtime environment will automatically detect that malloc returns a void star and can convert this pointer automatically to int star, for example, in this code example. Okay, so what is the big deal? Why do we need those conversion? In fact, why do we need at all to keep track of the type of a pointer? Couldn't we just say pointer instead of pointer on int, pointer on char, pointer on double? The answer is clearly no. To know why, take the following example. Let's say that I dereference p and I'm assigning the value 99 to the location that P is referring to? Well, here is my variable P. P is pointing to an int, 4 bytes. What happened? When I write the value 99 in binary, I'm going to fill enough zeros and 1 here over 4 bytes to respect the encoding of an integer. So it's not enough to know where my dynamic variable or my pointed variable starts at. I need to know also how long it is, and I need to know what is the type so I can use the proper encoding to write in memory the binary representation of my value. What happens if P is a double and I try to assign 99 to it? Well, first thing that's going to happen is a double is going to be 8 bytes instead of 4. So if I was just writing zeros and ones for the first half, assuming that P is an integer, P is pointing to an integer, I would be completely off. So the fact that P would be at this point a pointer on double would be a critical information to process the dereferencement of P and the assignment of a value at that location. I dereference P, I go at this address, but I know that I have 8 bytes here that I point to. Therefore, I'm going to write 99 over 8 bytes instead of 4. What's more, because I know the type of star P is a double, I'm going to be able to automatically cast 99 in its floating point representation and then use the appropriate encoding here to write a binary representation of a floating point number, okay, with exponent and mantis, instead of the binary representation of a simple int. So same goes with integer versus unsigned integer versus double versus float, etc. So this is why we carry all along this type information when we deal with pointers. It's not just a matter of having a pointer, it's a matter of having a pointer on something. For that reason as well, malloc use void star, and for that reason as well, your void star value will be converted to the type of the pointer P to make sure that everything is working. When you want to deallocate your memory, you call free with the pointer P. The pointer P evaluates into a memory address, let's call it alpha, okay, which was the memory address that you assigned to it and which was returned by malloc, and free is going to go at that memory address here and deallocate this portion of memory. Now you have to watch out. What does that mean to deallocate? That doesn't mean zero it, fill it with zeros. That doesn't mean really destroy it. That doesn't mean much. That means simply that from now on, that portion of memory is available for other calls to malloc to put their hands on. And that's really all it means. Which means, and this is a source of a lot of novice programmers' errors when first learning to deal with pointer, that means that if after doing free P you start to dereference P, you are going to probably still find at that address the data that you stored in it. There is no guarantee of it, depending on the implementation of C. I would certainly not recommend to do it. Once you free a memory address, when you free an allocated block, you need to consider it dead, regardless of what the current implementation of your language does. So every time you see a free pointer P, I would recommend that you add by yourself in your code P equal null. Why? Because that means I still have the address in P, but I don't want to keep it because it's the address of a block that has been freed, and therefore I cannot rely on this block being available, on this block holding my data. But once again, make sure you understand that free is not doing much work for you. It's not zeroing that memory, so the data is still there in memory until it's overwritten, okay? And it's just saying that that block is no longer guaranteed to be your sole property. So another call to malloc, for example, could obtain a portion of it and reallocate it to another variable. By setting P equal to null, how do we improve the situation? Well, as soon as a part of our code in which we forgot that we did the free to the pointer P is going to try to dereference P, as soon as this happens, dereferencing a null address will crash our program. So how does that constitute a positive outcome? Well, here's the alternative. It's either you crash your program the first time you try to dereference P, or because you didn't assign P to null, you are going to let this dereference go through, maybe overwrite data in a block of memory that has been partially reallocated for another purpose, and then good luck trying to track this bug. Okay, pointers related bug can become nasty very fast, extremely fast, so it's always better to crash your program abruptly as soon as somebody is doing something that is not 100% safe and legal, rather than let things happen such as modification of data at random location in memory and so on and so forth. The two other functions that constitute our dynamic memory allocation toolkit are realloc and calloc. We are going to use those a lot less. Realloc, like the name implies, is there to reallocate space. For example, using the previous code, you allocated an array of 20 integers, and suddenly you find yourself needing a little bit more room. So there are different ways of solving this problem. Okay, solving it by hand typically. Now, realloc offers you a way to solve that problem with a nice little API. What realloc is going to do for you, realloc is going to take as parameter your pointer towards the current area you allocated. It's going to take as second parameter the total size of your new array, including the 20 locations that I had. I want to go to a total of 30 locations, so I want 10 more integers in this array. So I call realloc with those two information, and realloc is going to do one of two things. Let me go back to the stack diagram. If some space is available after your array, realloc is going to allocate it so that you have a contiguous area now of 30 integers pointed by your pointer p. The address where those 30 integers start didn't change. If realloc cannot do that, realloc is going to find another location in the heap, possibly here, where it can allocate an array of 30 integers. This is the size that you requested. And once it finds such an area, it's going to allocate this area for you, copy the contents of the first array into it, and deallocate your previous array. And now P here is going to be assigned the return value of realloc. This return value of realloc is the memory address, and this is the memory address of the newly allocated extended array. So if the array could be expanded in place, this address would be the same as the current one of P. Otherwise, you would pass with P the current address, let's call it alpha, and you would get, as a result of calling realloc, a different address, beta, where your newly extended array is available. Once again, the conversion here, optional. Okay, if you don't do it by hand like that, if you're not an old school C programmer, well, the new C standard actually guarantee you that this is going to be done implicitly. calloc has a slightly different interface. It allows you to specify, instead of doing a malloc in which you specify I want the size of an int times 20, you have two parameters here where you can specify this is the size of one element of my dynamical array, and this is how many elements I want in my dynamical array. So very close to one another, okay, different API, different way of writing things. As an extra bonus, calloc is going to also make sure that all of your data allocated memory, is full of zeros. So filling with zeros a space of memory works well with integers, works well with unsigned integers, and so on and so forth. It doesn't work quite so well with a floating point number, sometimes depending on the encoding standard that you are using. So watch out for this. Like I said, we are going to mainly focus in this course on the two first function of this API. Okay, and every time you call malloc, realloc, or calloc, you need to include this call in a if statement. Why? Because if for some reason there is no memory available on your system, the only way that malloc has to tell you so is by returning the value null instead of a memory address. What happens if malloc returns null? Well, that means I could not allocate the memory on your behalf for one reason or another. What happens if you do not detect that malloc returned null? Well, you are going to try to use this pointer and you are going to cause a crash of your program with no explanation. So what I suggest you do instead is every time you need to call malloc, you need to do something like that. If p equal malloc, my apologies for the handwriting, size of an int, times 30. Every time you call a malloc like so to assign to a pointer a value, you are going to also test if the return value is equal to null. If it is equal to null, well, open curly brace, close curly brace, do something like p error. This is very basic handling of errors, but that would be enough for us. Malloc, how to say, returned null. That's a little message that is going to allow us to know exactly what happens. P-error is going to also allow the system to print out some error condition, etc. on the screen to give more information to the programmer. And once you are done with that, do an exit with an error code different than 0, for example 1. This is up to you. Exit 1 to notify that the program needs to stop right now. If you were developing production level code, you would have probably to try to handle errors at our level. So this is the way we handle error here. We just break out of the code cleanly with an explicit message telling us where it broke. And then we can go and investigate why it is that we didn't have enough memory to allocate an array of 30 integers. Okay, that's another question altogether.